Assalamualaikum and selamat sejahtera. Physics Form 4, Gravitation. Okay, my name is Cikgu Suryati Yusof, Sekolah Menengah Sains Muzaffar Shah Melaka. Okay. Today's topic is 3.3 Man-made satellites. Our learning standard is first, describe how an orbit of a satellite is maintained at a specific height by setting the necessary satellite's velocity. Second, communicate on geostationary and non-geostationary satellites. And third, conceptualize escape velocity. Right. Okay, this is the picture of the International Space Station or ISS, which can be seen from the Earth because of its large size and orbits at a height of 498 km. Okay, do you notice that this is a missile satellite? Okay. Missile satellite is difficult to be seen because of its small size and orbits at a higher height, that is 35,786 km. Satellites move in orbits at the specific heights and suitable linear speeds. How do man-made satellites help to improve human life? So let's begin our adventure with activity 1. Determine the linear speed of a satellite. So the first term is a linear satellite. So figure below shows the orbit of a satellite around the Earth. So this is a satellite which orbit around the Earth. A satellite moving in a circular orbit around the Earth experiences centripetal force, which is gravitational force. We have learned it in section 3.1. So given the data given is mass of the Earth is big M, mass of satellite is small m, radius of orbit of satellite equals to r. So this is the radius of satellite from the center of the Earth to the location of the satellite. Linear speed of the satellite equals to v, and the orbital period equals to t. Orbital period means the time taken to complete one orbit of the Earth. Okay, now what we have here is gravitational force between satellite and the Earth equals to centripetal force. Okay, so this is the force which made the satellite to move around what we call centripetal force. Okay, gravitational force, we have learned the formula from the first topic 3.1. F equals to G, gravitational constant, G, M, big M, small m over r square, equals to centripetal force is F equals to mv square over r, where v is the speed of the linear speed of the satellite. Now what we can do is, since this is equal, so we can cancel small m and r. Okay, what we get is mv square over r equals to g m over r square. And from there we have v square equals to gm over r, and v is equals to square root of gm over r. So the first formula for this subtopic is linear speed equals to gm over r. Okay, so v equals to square root gm over r. Okay, so gm is constant. Okay, G is the gravitational constant, M is the mass of the Earth, and then linear speed V will depends on the radius of its orbit. So it depends on the radius of the orbits. If the satellite is at a high above the surface of the Earth, okay, so this is a satellite. Okay, so H is the height from the surface of the Earth to the location of the satellite. Therefore, r, the small r, equals to radius of orbit equals to r, capital R plus h, where r is the radius of the Earth. So here, from here to here is the radius of the Earth plus the h, right? Okay, so linear speed of the satellite v will become v equals to square root gm over r, big R plus h. Remember, r is the radius of the Earth and h is the distance from the satellite, location of satellite to the surface of the Earth. So, okay. Now, what is the requirement so that a man-made satellite can be launched to keep orbiting at a specific heights around the Earth at radius orbit r? Okay, so what is the requirement so that we can launch the satellite? So the answer is the linear speed of the satellite is v equals to gm over r plus r. Means that the satellite must obtain the speed of value. This is from the value of this formula. Okay, so it must exceed this linear speed value. Okay, so let's try to do one question. Okay. Okay, a GPS satellite is orbiting the Earth. Okay, this is a GPS satellite orbiting the Earth. Calculate the satellite linear speed if it is at an altitude of 20,200 km. Given that r is equals to 6.37 times 10 to the 7 meter, g equals to 6.67 times 10 to minus 11 Newton meter square kg minus 2, and mass of the Earth is 5.97 times 10 to the power 24 kilogram. So we have to calculate r. So r means the radius of the Earth, 6.63 times to the power 6 plus 2.02 times 10 to the power of 7. This one, this one. Oh, this is kilometer, so I convert to meter. So times 10 1000, so that's why I get this. Okay, so these were 2.02 times 10 to the power of 4 times 10 to the power of 3, you get 10 to the power of 7. And you calculate by using calculator, so you get this answer. Next, the next step is insert into this formula. So G is 6.67 times 10 to minus 11 times 5.97 times 10 to the power of 24 divided by 2.657. Okay, and then you take the square root, and the final answer is 3.87 times 10 to the power of 3 meter per second. That will be the linear speed for the satellite in order to make sure it will orbit the Earth. Okay. So what will happen to the satellite if the linear speed of satellite is less than the required linear speed? So the satellite will fall to a lower orbit and continue to revolve towards the Earth until it enters the atmosphere. The movement of the satellite at a higher linear speed against air resistance will generate heat and cause the satellite to burn. Okay, so it is dangerous for the satellite and it will burn, okay, because of the heat generated. Okay, now we move on to activity 2. We have the word to compare between geostationary and non-geostationary satellite. So man-made satellite, we have two types. The first one is geostationary satellite. The second one is non-geostationary satellite. So look at this picture diagram. So we have two satellites, satellite A and satellite B. So the first one, we are going to talk about geostationary satellite. So what are the characteristics of the geostationary satellite? Okay, first, a satellite that moves around the Earth at certain height in a special orbit named the geostationary Earth orbit. So it had a move around at certain height. Okay. Okay, next. Move around the Earth in the same direction as the direction of the Earth's rotation on its axis. So let's say the Earth move in this direction, so the satellite also will move same with the Earth's direction of Earth's rotation. Okay. Okay, third, orbital period T equals to 24 hours. So we know that the Earth will the period of rotation of the Earth is 24 hours. Okay, so the Earth will spin in 24 hours, right? And then, so the orbital period of the rotation of the satellite equals to 24 hours. Okay. And lastly, always above the same geographical location. For example, so this is the location on the Earth. The satellite must be always above X. So okay, you make sure that that's what is called stationary. Okay, so let's say this is the location on the Earth. So make sure that the satellite always follow the the rotation, the location on the Earth. Okay, so that is characteristic for the geostationary satellite. Okay, now we move on to non-geostationary satellite. So let's say this is satellite B. Okay, remember just now the satellite A move around what we call geostationary Earth orbit. Okay, a satellite that move around the Earth at changing orbit height. Okay, normally in a lower or higher orbit than the geostationary Earth orbit. So it has the Earth orbit always change. Okay, either lower than this orbit or above than this orbit. Okay, orbital period is shorter or longer than 24 hours. So let's say it's lower, it should be less than 24 hours. If above, it should be more than 24 hours. Above different geographical location at different times, so it does not depends on the location on the Earth. So it have its own pace, right, time to move around the Earth. Okay, so let's look at the similarity and difference. Okay, first the similarity are orbit the Earth. Both satellites will orbit the Earth. Okay, and secondly, both have the linear speed. That is the formula, and the period is equals to 4 pi square r cube over gm. Remember, we have learned this in 3.1. Okay. Okay, now we look at the different characteristic of geostationary satellite and non-geostationary satellite. So we have a few aspects here. The first aspect is direction of motion, period, position. Okay, look at the direction of motion. So direction of motion same as direction of Earth's rotation. Okay, direction of motion same as the Earth rotation. Okay, the period T equals to 24 hours. Here, above the same geographical location, communication satellite. The function of here is for communication satellite. For example, is MISAT. Okay, now we look at for non-geostationary satellite, direction of motion need not to be the same as direction of the Earth's rotation. Okay, period can be shorter or longer than the 24 hours. The position of different geographical location. Function is Earth imaging GPS or weather forecast. Example, so we have Tiongsat, Razaksat, Pipit or ISS. So these are the difference between the geostationary satellite and non-geostationary satellite. Okay. Okay, next we have what we call escape velocity. So this is the last part. So what is the meaning of escape velocity? So escape velocity V is the minimum velocity needed by an object on the surface of the Earth to overcome the gravitational force and escape to outer space. Again, minimum velocity needed by an object on the surface of the Earth to overcome the gravitational force and escape to outer space. Means that if the speed is lower than the escape velocity, it cannot overcome the gravitational force and cannot go outer space. When the escape velocity is achieved, when the minimum kinetic energy of an object is able to overcome its gravitational potential energy. Okay, the minimum kinetic energy of the object is able to overcome its gravitational potential energy. Alright, so let's do some calculation. Okay, so derive the formula for escape velocity. Right. So we have an object at a distance r from the center of the Earth. Okay. Mass of object is m, and mass of the Earth is big M, capital M. Okay. Now the kinetic energy of the object is half mv squared. Okay. Second, the gravitational potential energy of the object is given by G, capital M, M over R. Okay. This is the given formula for gravitational potential energy, and from there we have minimum kinetic energy plus gravitational potential energy equals to 0. Okay, I think this is conservation of energy. Yeah. Okay, so now we have is half mv squared plus minus G mm over R equals to 0. 0. have the V square equals to 2gm over r from here, right? Bawa sini, bring here, and 2 bring to here, so we get V square equals to 2gm over r, and we have the formula V equals to square root 2gm over r, where g is the gravitational constant, m is the mass of the earth, r is the what we call the distance between the center of the earth to the object. Okay, let's try to calculate the escape velocity from the earth. So if you want to escape from the earth, so what is our escape velocity? So we have the formula mass of the earth, radius of the earth, right? So we have the formula V equals to 2gm over r. Okay, so we substitute 2 times 6.67 times 10 to minus 11 is given. This is the mass of the earth, and this is the value of the radius of the earth. So this is, we want to find at the escape velocity from the earth means the object is at the surface of the earth, so r equivalent to the radius of the earth, because the object is on the surface of the earth. That's why we have this formula, this data given, and we calculate when we got V equals to 1.12 times 10 to the power of 4 meter per second. It's about 11,102 120 meter per second. Okay, it's quite big value. Okay, so state factors affecting the escape velocity. So it depends on the mass of the earth, or the mass of any planet, divided by the distance of the object from the center of the earth. Alright, now we will discuss the benefit and implication of escape velocity. So we try to discuss 3 problems. Okay, first one is why the earth can maintain a layer of atmosphere around it. So around the earth's surface is the atmosphere molecules, the air molecules. The air molecules cannot escape. Why? Okay, so high escape velocity of the earth is 11,200 meter per second that we calculate just now. And the molecules in the atmosphere move at the average linear speed of 500 meter per second. Okay, it's a small speed compared to the high escape velocity of the earth. Therefore, it's lower than the escape velocity from the earth. So air molecules that are moving randomly were not able to escape from the earth into outer space because its speed is lower. Okay, next question. Why commercial aircraft cannot escape into outer space? Okay, aircraft this is not rocket, this is ordinary aircraft. So commercial aircraft can fly a linear speed of 250 meter per second only. Okay, alright. So fighter jet can achieve supersonic linear speed of up to 2,200 meter per second only. So both their linear speed are lower than the escape velocity from the earth. That is what, 11,200 meter per second. Okay. And last one, how can a rocket achieve escape velocity from the earth and send the spacecraft into outer space? Yeah. So the answer is the launching of rockets requires large quantity of fuel to produce high thrust that enables the rocket to achieve escape velocity of the earth. Hence, it can send the spacecraft into outer space. So this rocket will give you thrust, okay, the thrust bottom here, and we will have it will push the rocket to accelerate with high velocity, high speed, and it will be more than 11,200 meter per second. Okay. Okay. Next, we want to solve problems involving escape velocity. So one of the questions asks you to find the escape velocity for Venus, Mars and Jupiter. So we have calculated for the Earth. So what we do is use the formula V equals to 2gm over r. Remember, r is the radius of the planet. Okay. So for example, Venus 2 times g, okay, time mass 4.87 10 to the power 24 divided by 6.05 times 10 to the power 6, and I have calculated, and the answer is 10,362.5. For Mars, 5,000 18.9 meter per second. For Jupiter is 60,216.6 meter per second. The Earth is about 11,200 meter per second. Okay, so these have different factors. Okay, the higher the mass, the bigger the planet, so the escape velocity should be bigger. Okay, so next, so we have one question. The moon and the sun are two bodies in the solar system, right? So we have moon, we have a sun. Given the mass and also the radius, so we have to calculate the gravitational acceleration on the moon and the sun. Okay, first we calculate the gravitational acceleration G. I think we have do this in topic 3.1. So we do it again. So G equals to big G the big M over R square, where R is the radius of the planet. So 6.67 times 10 minus 11 times 7.35 times 10 to power of 12. This one. Divide by the radius, 1.74 times 10 to the power of 6. And do not remember, please square. You have to square the value. So you get the answer 1.62 meter per second square. So for the sun, you do it just like just now, and you get the values 274.0 meter per second square. I think in our Earth is what, 9.81 meter per second square. So we have here the moon has low gravitational acceleration compared to the sun because its mass is lower and the radius is also lower. Okay, now calculate the escape velocity from the moon and from the sun. Okay, so we calculate by using this formula. Okay, just now. And we get for the escape velocity for the moon is 2.37 times 10 to the power of 3 meter per second. And for the sun is about 6.18 times 10 to the power of 5 meter per second. It's about 600,000 meter per second to escape velocity from the sun. Okay, so the moon has low escape velocity compared to the sun because the mass of the moon is smaller than the sun. Okay. Discuss whether escape velocity from the Earth for spacecraft X of mass 1,500 kg is different from spacecraft Y of mass 200 kg. So both want to escape from the Earth with different mass. Okay, so remember the formula. V equals to 2gm over R. So m is the mass of the Earth. So the answer is the escape probability should be the same because mass of the satellite does not affect the escape velocity. What effect is the mass of the Earth itself. Okay. Now we have the satellite orbits the Earth at the height of 700 km. What is the linear speed of this satellite? Okay. So now you have asked you about linear speed. So linear speed. So this is formula just now. Linear speed. Do not confuse with the linear speed and escape velocity. Okay, for escape velocity tadi square root 2gm over r kan. For linear speed is gm over r, where r is the value of the radius of the Earth plus the height of the satellite from the Earth. Okay, so you insert all the value, all the information, and the answer is 7,504.82 meter per second. Okay. Okay, that's it for our lesson today. Thank you for listening to the lesson. I hope you understand. Okay, see you next time. Thank you. Assalamualaikum. Bye.